Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my continuing feature on the Math Lovers book. And for the last several lessons, I've been talking about logic, in particular Boolean algebra. And I think the last two lectures were on truth tables. And today I'm going to talk about an important application of truth tables, namely tautologies and contradictions. Tautologies are just logical expressions that are always true, and contradictions are logical expressions that are always false. So anyway, let's begin. So yeah, that's just what I said they are. You can think of them as Boolean functions, but they're constant functions. They're either always true or they're always false. Um, and remember, true and false are the only possible truth values of any logical expression. In general, you're going to have some cases that are true and some cases that are false, like the ones I was going over yesterday. But in this case, they're either all true or they're all false. Anyway, it's probably best to look at some examples. So, the first example I'm going to give is the logical expression P or not P. And I think just from the form of this expression, it's pretty clear this is tautology. I mean, any logical statement is either true or false. That's not quite true. There's some weird ones like this sentence is false. That's Epimenides' paradox or the liar's paradox, but I'm not getting into that here. Most statements in the world are either true or false. If they're true, then their negation's false, and vice versa. So remember, not P is the opposite. So an or is always true if either one of the things on the thing on the left is true, or the thing on the right is true. Well, it's obvious that either P is true or not P is true. So therefore, P or not P is always true. And you can look at the two possible cases if you like. There's only two cases to look at because there's only one variable here, P, that's either true or false, in which case not P is false or true, respectively. So that's pretty obvious. And another one that's very similar is P and not P. But this one's a contradiction because it can never be the case that a statement's both true and false at the same time. Um, I think that's what's called Aristotle's law of excluded middle. There's a lot of names for this, but something can't be both true and false at the same time. That's like a yes or no paradox. Um, uh, Next up, the most common time travel paradox is kind of a yes or no paradox, a grandfather paradox. I don't know if I should get into that here, but well, since I started talking about it, I as well continue. So the grandfather paradox is: imagine you had a time machine and you could travel back in time to a time before you and your parents were born, and then you decide to go back in time and kill your grandfather. Well, assuming that the timeline's fixed, you can't do that because that means you wouldn't be born and you wouldn't be able to take the trip to begin with. That's a yes and no paradox. Either you kill your grandfather or you don't. Either you exist or you don't. So that's an example. But yeah, so and very similar analysis to P or not P. P. Again, we only have one variable P that's either true or false, in which case not P is false or true. But remember how and conjunction works? It's only true if both sides are true. But in both of these cases, one side's true and the other side's false. So that means P and not P is false in both of those cases. So that's a contradiction. Contradiction is just the opposite of a tautology. And the negation of a contradiction is a tautology, and vice versa. But anyway, now I'm going to give some more complicated examples, but these are important examples. So, how about P or Q implies P? And I think this is another one that's kind of obviously true in all cases. If P or Q is true, then that means remember the only time that an implication can be false is if the thing on the right is false. But how do I say this? Yeah, okay. Well, it's probably just better to look at the cases here. There's four cases for this one. true, 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 false, false, true, and false, false for P and Q. And the way OR works to remember, this is P and Q applies P. I'm sorry, I made a mistake here. Yeah, I think, yeah, but that's why I got confused. If P and Q are both true, then P is obviously true, right? Because P and Q can only be true if both P and Q are true, which means P is true. So that's all this thing is saying. And you can go through all four cases here. P and Q is only true when both P and Q are true. The first row, the second through fourth rows are all false. But remember, that how do I say this? P or Q to find, so then you have to look at P or Q is true in the first row, and P is true, so true implies true, that's true. False implies true, that's also true. These are the controversial ones. Remember I said we have to kind of make an arbitrary definition for implication in the case in which the antecedent's false. Well, by default, the conclusion's true because we kind of have to have it be something or other. So, it really doesn't make sense to talk about the implication of something that's false, but by default, according to the way we defined if then, if the antecedent is false, the conclusion is always true. And so in the last three cases, the antecedent is false, therefore the conclusion is true. So P and Q implies P in all four cases, therefore it's a tautology. And one more example I'll give you. How about P implies P or Q? This is kind of similar to the last one. And again, we can go through all four cases of P and Q. And in this case, the only time in which P or Q is false is when both P and Q are false. In the first three, P and Q are true. P or Q is true. But now we have P on the left. So true implies true for the first two rows, and true implies true is true, and also false implies anything is true by the way we've defined implication. So the last two rows are also true by the way implication is defined, or the antecedent's false. So this is another logical identity. By the way, I'm kind of jumping the gun here, but tautologies are also called logical identities, and we're going to use a lot of those later. These are important tools in making logical arguments. So we remember how a logical argument goes. I haven't talked about those yet. They're sort of like the syllogism, Aristotelian syllogisms. The first for the syllogisms, there's like 3 or 4 lines for each of them, and every line except the last are the premises, and the last one's a conclusion. So a logical argument is just a set of premises, and then you use certain rules of logic to arrive at a conclusion. And some of those rules of logic are called logical identities. And that's just a fancy name for tautology. So all these tautologies I've shown you today. P implies P or Q, that's one of them. P and Q implies P. One of these was a contradiction, but the first one is another logical identity, P or not P. So we can use those in our toolbox for proving things in logic. Anyway, that concludes my video for today on tautologies and contradictions. So thank you for watching. Long live math, and I'll see you guys next time. Bye.